Yeah, very good afternoon, and welcome back to our first lecture on design of domes. This is going to be the last chapter, and in this chapter, we'll be discussing on especially the design and the detailing of the spherical and conical domes. It's a structural point of view. We have only two types of domes. One is because here we will be dealing mainly on spherical and conical domes. Yeah. So this is our flow of this lecture. Introduction, types of domes, forces in domes. I mean forces in domes actually. It is a dome. Forces in domes. Then finally the design of domes. Okay. So let us see one by one. So in general, if you in general, if you ask what is a dome, it is like dome is a structural element. For example, if you see, let us say, this is a bottom portion, and let us say we have a arch like this. The center it is here, and it is like this. Let me make it clear. It is like this. Okay, and if it rotates like this, to the circumference of this circle or whatever it is, then we will be having a dome like this. A dome will be formed like this. Okay, so this is called a dome. We can say that this is structural way, or mathematically how does a dome form. This is how it is. Okay, around the circumference of a circle, if an arch rotates through the center as an axis of rotation, then a dome is formed. As you can see here, these are the few types of domes we can see. Because from the, if you see the history of the domes from long before all over the world, even the prehistorical time and all over the world, this structure is a common actually. This is using the hatch, and you can see the light, because initial time that there was no electricity and all. So to get the sunlight, they used to keep a opening here at the top of the dome, the crown of the dome. This portion is called lantern, lantern. This is, as you can see, this is the world famous Taj Mahal. This Taj Mahal is mainly famous because of the aesthetics, and for that aesthetics, the dome has got its own importance here. Without dome, the architecture would this architecture of this Taj Mahal would not have been like this. Then coming to the next, mainly we will be discussing in a peripherally we will be discussing actually on these materials which we use for the dome. It is made up of mud, snow, brick masonry, stone masonry, wood, concrete and steel. These are the mainly, and nowadays using composite material also domes are being prepared actually, manufactured, like glass reinforced concrete, GRC and all like this. But here our scope is mainly limited to, in this syllabus, in chapter, scope is mainly limited to concrete. Okay, these are the main different types of domes, architectural point of view, aesthetic point of view: corbel dome, cross arch dome, geodesic domes, onion domes, oval, rotational domes, saucer type, umbrella type, cable and net, and inflated domes like that. So I will just show you some figures so that you will get an idea of that. These corbel domes are mainly made up of bricks, like if you see one brick here and with a small projection like this, so at last it will form like a dome here actually. These are all corbel domes. As you can see here, this is a corbel dome made up of bricks, and this is a cross arch dome actually, because inside you can see, as I told you, if an arch is rotated, the dome is formed. So like that, there are a lot of arches are there. Is called cross arch domes. These are all come under the category of architectural, okay, types. Okay, this is geodesic dome actually. It is mainly made up of nets, with the triangles. completely, and it's made up of concrete, not concrete mainly, it's made up of like a plastic or fiber like that. These are all your onion domes, because these domes are especially in, it looks like an onion. As you can see before, even the Taj Mahal portion, it is also just like an onion dome actually. It's exactly in the shape of an onion. Okay, this is a oval type domes, and a cup and saucer you would have seen actually. So this is exactly replicates the saucer, so it's called saucer dome. The umbrella type dome is old churches and all, you can see this umbrella type, especially in Europe and all, you will be seeing these umbrella types. Cable and net domes, okay, it's made up of steel, otherwise cable, all these things and all. So these are all general you are supposed to have basic idea of what are the different types of domes actually. This is all our architectural point of view. These are the varieties, various types of domes actually. And when you come to the structural, here we will be discussing mainly on spherical domes and conical domes actually. This is in the form of a sphere, and this is in the form like as a cone actually. It's conical dome, the section of the dome looks like here. This will be the concrete. Okay, this will be mostly hollow, and sometimes what happens over the sphere, they will be having some as you can see, as I have shown here, yeah, in the here, just like it's called lantern, lantern, lantern. It's mainly for a skylight and all. Okay, so the main advantage is why these domes are mainly attracting the people or the structural engineers. The main thing is it can cover long spans actually, because even if a beam and all, you have a limitation for a normal RCC beams, if it is unless it is pre-stressed concrete. But whereas the long spans can be possible with the domes actually, and domes are having only axial forces, mainly compression and tension, and there will not be, or the bending moment and shear force is very negligible actually, especially in the case of domes. So that is a structural advantage for us actually. As far as the bending moment and shear force is very less, the thickness will be very less, and reinforcement will also be very less actually, because deflection will be very less if the bending moment is less. So the thickness is very less, because if the thickness is very less, so less reinforcement is required. Then aesthetic point of view, the domes are very good actually for seeing, as I told you in the case of Taj Mahal. It is very beautiful for the eyes, only mainly because of the domes, how the domes are arranged. Okay, and domes can cover a large area also. So it's like a long span can cover a large area. These are the main advantages by which a structural engineer one will go behind the domes. And some of the disadvantages, like the construction is going to be a bit difficult because of the shape like this, and formwork and all these things are difficult, and thickness is very small. Concreting also and reinforcement also, placing and all things will be a bit difficult actually, because lots of congestion might happen if you have not done it properly. So these are the some disadvantages, mainly the domes. Okay, so let us come to the forces in the domes. Comes to so you can imagine a small ball which has been cut in the middle, and it has been placed like this, upside down like this. Yeah. So you can see here, suppose we apply a load here, let it be, if it's a point load or whatever it is, a load here, what happens, this will be transferred through this. So these lines, okay, which are perpendicular to the diameter, these are called your latitude, meridians actually. These are called meridian. Okay, and the circles around the dome, these are called latitudes. Okay, so there will be mainly two types of forces which a dome will be subjected to because of the loads. Okay, this one force is along the meridian. Okay, along the meridian, it is called meridional thrust. Okay, and another one is along the circle or along the rings, which is called hoop force. So the two types of forces, one is along the meridian, okay, which is called meridional thrust, which is normally denoted by T, and another one is along the circle or rings, okay, that's called hoop force. So these are the two forces which a dome is subjected to. As you can see here, when if you can imagine, I want you to visualize like you are taking a ball like this and you are applying a force. It is be a plastic ball or rubber ball, and you apply this. So what will happen is, if at all it breaks, it will be breaking at the bottom only mainly. It will be breaking or it will be tearing like this, start tearing from here actually. So the main thing is that normally uh, in the domes, this you can see here the meridional thrust is normally a compression in nature. Most of the cases it's a compression, and the hoop force H, this is compression here, and some at the when it comes to the bottom it's called it is in tension actually. You can see here it is a tension. So this portion, this band is called tension band, and you can see this circle or this what you call it as this ring. Okay, this is the ring which divides compression. Above here it is a compression, and below it is tension actually. Okay, so you can see that as I told you, the meridional thrust is mostly it is in positive. Okay, most of the cases, whereas the horizontal one, the hoop force will be, it can be compression, okay, which is positive, and it can be tension, which is negative also. Okay, so mostly the tensile force will be below this one particular area, close to the periphery of this one, so particular circle. Okay, so if I can show you like this, so let us say if I take a cross section of this one, you can see this line, this red color one, let it be this one, this band. Okay, it's like this. So above which it is a compression, this is a theta, above which it is a compression, where your H is compression, and below which it is a tension, negative it is. So our main aim is to find out how do you find out this tension and compression. And another thing is that they'll be having a hoop tensile forces, as I told you sometimes here, this hoop tensile force, and vertical and a lateral load transferred down from here, as I told you here, because this the dome will be resting on a beam actually, it's called ring beams. Okay, so this vertical load and horizontal force will be transferred to the beam. Okay, so our main aim is to find out how do you find out meridional thrust and hoop forces T and H. Okay, so this is what it is. You can see here, this is your so as I explained before, because this is one ring, this is another ring horizontal, this is another ring through which your hoop stress will be there or hoop force will be there. So how the load is transferred is the weight of this ring is transferred to this ring, and it's transferred to this ring, at last it goes down actually. Okay, and because of this the weight, there will be a force like this tangential to this through the meridian actually. This is called thrust T. Okay, and you will be having a T, actually it is T plus small dt will be there, because I will tell you what it is, because I have shown here, we'll see in the next slide. T plus dt will be there, because and you can see here these are all the horizontal rings actually, because as I told you this load is transferred to this one, and here to here, here to here, here to here, it goes like this, it comes down actually, and from this it transferred to the ring beam. If I take a cross section, it is like this, you can see here. If I take a section here like this, it looks like this. So this is your T along the meridian, it comes here like this T, and at the bottom if you see this is a horizontal force, hoop force, and if you take a small portion along the circumference of the or the body of the surface of the dome, you can see here this is your meridians and this is your latitudes. Okay, along the latitudes you have a horizontal force, hoop force. Along the meridian you will have a thrust, meridional thrust T. So it comes here like this, and as you come down sometimes here at the bottom, okay, as I told you, you comes at the bottom here, your H will be instead of here your H, if you take a small portion closed, so here your H will be tension T. Okay, not compression. As you can see, it is compression, but here tension. Okay. So generally, this is a general cross section of a dome. Let us see, this is inside it is, okay. So this is, let us say, one ring A, B and C, D. Okay. So as you can see here, because of the weight of the dome, there will be a horizontal thrust will be there, which is along the meridian actually. This is called meridional thrust, which is T, which is acting on the ring like this here, and for the equilibrium it will be, one will be there in the opposite direction also, but at the bottom it will be T plus dt. Why? Because this thrust will be there. In addition to that, the weight of this band will also be there, A, B, C, D, because of which will be T plus dt, and this angle is theta. As you can see here, here it is theta, and here it is d plus theta plus d theta. Okay, so this is the two forces T, and one is on the band actually, it is H. So it will be like this. So as I told you, as you come down, it will be positive here. All your H is compression in nature. This top portion is called crown. The H is a compression. The blue color line is a compression. And when you come down, it is in tension. H will be in tension. So you will be having H, hoop force H. Okay, it's compression which is positive, compression C, and H will be negative, which is tension. Okay, so as you can see here, this, let us assume that this ring, this band is the band which divides tension and compression. Okay, above which it is a compression and below it is a tension. Okay, so you can see that if I take a center vertical axis, and this angle theta, okay, from this like this angle is theta. I can show it in, okay, theta. So you can see that above this theta, this line, if the theta is small, okay, so let us say some particular value. The theta is, as you go down here, theta will be small. So when it reaches here, it will be 0. Okay, then it will increasing, that will reach here. Okay, then again it reach. So this particular value, it has been noted that we will see how it is getting, but time being 51.82 degree, that is the value. The theta is less than 51.82, the value of the nature of the force H will be compression, and if it goes more than 51.82, then it will be in tensile in nature. Okay, so we will see, as you can see here, actually this is how it is. Okay, I'll come to that in detail. So you will be having two cases, like one is dome with the UD load. What is the UD load? It's a sulfate itself, and some people are working over that one. Okay, so UD load will be permanent, it will be there. A dome without a UD load is impossible actually, and it is a point load. How does the point load comes? Point load comes in this case actually. As you can see here, if there is a lantern is there, there will be an opening at the top also. If lantern is there, then it will transfer point load actually. Okay, so dead load is a constant. It is by default it will be there, whereas point load, if it's a lantern is there, then automatically the point load will come. So dome might experience either dead load, UD load, otherwise both, combination of UD load and point load. Okay, alright. So if it is only a UD load, then there is no point load, then the meridional thrust, this T is found out by WR by 1 plus cos theta, and it is a hoop force H is found out by WR into cos square theta plus cos theta minus 1 divided by 1 plus cos theta, where W is the UD load, R is the radius of the dome, and theta is the angle which we are discussing about. If this is the point, if you are considering at this point I want to find out what is the T, okay, then this will be my theta. If this point I want to find out what is the T, then this will be my theta, like that. Theta vary from here to here, right? Here theta will be 0 because it is at the angle, it is at the axis theta, and theta keep increasing, okay, like that. and if it is a point load, then your meridional thrust will be W, capital W by 2 pi r square sin square theta, whereas r and theta and everything is the same what I told in the previous case. And hoop force H will be minus W cosec square theta by 2 pi r, where minus is because it is negative, it's a tension always. So here one thing you should remember is, as I told you here, at this particular point where theta is 51.82, okay, right, above this it is a compression, below this it is a tension. So I want to know, because as I told you here, it is a compression and it's coming, compression is positive, then it has to come to reach 0, then it will be negative, correct? So one point of time that H will be 0, that is the meaning of that. Okay, when I say it is above this, it's H is compression, means it have positive value, it is a negative value. So transition from positive to negative, it has to come through 0. So one point where the H should be 0. So I want to know which place that H is equal to 0. So for that, it is very easily we can find out. You substitute H is equal to 0 here, so that you will get theta is equal to 51.82. Meaning is that at 51.82, your theta, or you can see it down, this will be the easy. At 51.2, you can see here, it is 0 here, 10 degree, 20 degree, 30 degree, and it at last it comes to 51.82. At this point, H will be 0. And above this point, here it is H will be compression as shown here. Below that, it will be tension. And if it increases, the theta value increases 51.82 degree, then the value of H will be, magnitude of H will be in tension. Okay, then let us come to we want to know what is the maximum value of H. Okay, so we know that the cos theta, cos 0 is 1 and cos 90 is equal to 0. So it is if you provide theta is equal to 0 here, then you can found that H is equal to WR by 2. So this here it will be the maximum. Theta is 0, then H will be your hoop force will be WR by 2, okay, at the crown, at the axis crown here. Then as theta increases 10 degree, then your H value will reduce 20 degree, theta is 20 degree, then if you substitute here all these things, then H value will reduce, and when it reaches to 51.82 degree, your H will be 0. Then when it crosses that, if the theta value is more than 51.2, then H value will change sign, okay, minus, it will be tension, okay, then it keep increasing like that. So this one you should keep in mind. The maximum value of H is when theta is equal to 0, it will be happening at the crown, and the magnitude of H is WR by 2, okay, and the H will be 0 at theta is 51.82, and from 0 to 51.82 degree theta, the H will be compression in nature, and once it crosses 51.82 degree, it will be in tension in nature. So these things you just keep in mind. So this is with this, and another thing is that whenever we do a problem, okay, now let us see another case. Let us see, you are talking about the UDL. I will come to that in point load in another. How does it come? So if a DOM is subjected to UDL on point load, then how do you find out the T and H? So it's as simple as that. Just add this. Means in a DOM, if a DOM is subjected to UDL and point load, then the meridional thrust T is equal to T due to UDL plus T due to point load. That is WR by 1 plus cos theta plus W by 2 pi r square sin theta. And same is the case with hoop force also. So, and what we do is we will find out this whenever we design a DOM. What we do is we will find out T and H for all values of theta. Means we will start with 0, 10, 20, 30, 40, 50, 60 like that. We will find out up to this, and we will find out which is the maximum value of that one. That one we will take it, and for that we will find out area of T. Okay, that is how we do. So this is what. So this one you can remove it. So some books they have taken 5 degree also, which is not required. You can start with 0, 10, 20, 30, 50 like that till the maximum value of theta. What is the meaning of maximum value of theta? maximum value of theta is, let us say this is your dome. Okay, this is your dome is going to make it only at this point. Okay, this is your, what I say, this is your slab here only. Okay, but your dome is part of a circle, correct? No, so maybe somewhere here is your what I say, center. So this might be your radius. Okay, this is not your radius. Okay, that you just keep in mind. This is not your radius. This or this. This is the center point like this. This is A. Let us say this is B. AB is not your radius. Radius is AC actually, or OA. AO is the radius. This is the the radius of the part of the dome. This much radius only we are going to construct the dome, but the actual radius will be this one, because this is not a complete sphere, it is a part of the sphere, so radius will be somewhere here. Okay, so that one, this finding out radius is important, that AO, that is important, that is important one. Then you can see here, so as we discussed in the previous one, this is how we do that. We'll find out meridional thrust and hoop forces actually. So T, so this W R by 1 plus cos theta, because W and R is according to our problem 1 plus cos theta, that one you will find out these values 1 plus cos theta for 0 degree, 10 degree, 20 degree, like that. This is, don't worry, 1 plus cos theta, because we know that what I say, this one, how they have mentioned is sin square theta. You know that 1 plus cos theta minus 1 plus sin theta. Because this 1 minus sin theta, 1 minus theta cancel. That is how it is coming here. Instead of 1 by 1 plus cos theta, they have mentioned here like this. Okay, both are same only. All right. So this coefficients we will find it out. 1 by 1 plus cos theta. In this case, W and R we will forget. We will, and cos square theta plus cos theta minus 1 divided by 1 plus cos square theta, 1 plus cos theta, that this one we will find it out here. See, as you can see here, this values, this coefficients we will find out, especially for T also at the same time, for H also. This is for T, this is for H. In this case it is concentrated load is coming there, we will do it separately. Okay, then add after this, which is the maximum, we will find it out. When you do a problem, you will understand. Before we wind up, so these are the things, some points on the domes. Domes mainly subjected to axial forces only. As you can see, as we have seen, only compression and tension forces, bending moment and shear force are very negligible in domes. Steel reinforcement is less in domes. Thickness is comparatively less. Normally we take 75 mm to 150 mm, not more than that. Domes can cover large area, even 15 to 20 meters we can cover domes. Normal loads coming in domes are live load, dead load and wind load, snow loads also. But the analysis, because of the peculiarity of the shape of the dome, the analysis of a wind load is very tedious actually. So in order to take care of this one, these loads, wind loads, normally we take 1 kilonewton per meter square to 1.5 kilonewton per meter square. We add it additionally in the UD load actually. So okay, so because then wind analysis is going to be very complicated and complex. As the forces are axial in nature, the reinforcement is provided in the middle of the thickness. That is what. Then another thing is dome is designed following the working stress method. Okay, so what is the explanation of the point 8 is, your dome is like this actually. Let us say I take this is a dome. Okay, one point and another point. This is a thickness. Okay, we make it a bit bigger so that it will be easy for you to understand. Like this, let us say this is a dome. Okay, and this is the slab. Okay, and let us say this is where it is going to be resting actually, because wherever it rests, normally we provide a small beam like this. This is called, because your dome will be resting on the beam actually. This is called what you call, it is called the ring beam. Okay, like this. Well, this is called ring beams actually. This will be resting on the beams. Like this. So this is the beam. Okay, it's called ring beams. Okay, ring beams. Yeah, and what will happen is, because as I told you, this only tension and compression, so your reinforcement will keep it at the center actually, exactly at the center of the dome. So if the thickness is 100, then at 50 we will keep the reinforcement here like this. First you will be having your what you call, your reinforcement for the meridian, then you will have your this one, hoop reinforcement. You will see how to give the reinforcement. Okay, sometimes what will happen is, there maybe some lanterns will be there, as I told you before. This is your dome, this is your dome like this, and sometimes what will happen is, you will be having, because this is your thickness of the dome. Okay, so here what will happen is, there will be some lanterns will be there to take care of horizontal light, skylight like that. They will provide a lantern like this. In this case what will happen is, we need to provide a small beam here also like this. They will provide a small beam like this, because the lantern will be resting on the it's a beam. Okay, this is also called ring beams. This is called upper ring beam, and when you have a ring beam at the bottom, it is called a lower ring beam. It's also ring beam. This lower beam, ring beam, upper ring beam. Okay, so when you design a dome, you are supposed to design these ring beams also, this and this also. Okay, so I think we will see the design of the domes in the next class. I hope this is clear. Thank you very much.